Welcome to this educational talk. I'm going to tell you about the effective field theory description of the resonant scattering. First, I would like to remind the examples of resonances in the particle physics and describe the possible complications in their theoretical description. Then I'm going to outline the algorithm to study the resonant scattering of two particles. Next, we will construct an effective field theory of the elastic fermion scattering in the resonance channel with a scalar exchange. I'm going to concentrate on details of the leading order Lagrangian for each interacting field, and will briefly discuss the theory at the next leading order. At the end, I would like to present the results for the resonance curves or line shapes. Let's start with a small historical overview. In particle physics, the peak in the differential cross-section of scattering experiments, located around a certain energy which is plotted on x-axis, is called resonance. Such peaks are associated with subatomic particles and their excitations. The first resonance, the delta resonance, was discovered in Chicago during the early 1950s by Enrico Fermi and his colleagues in the pion-proton scattering on the proton cyclotron. Plenty of excited baryonic resonances, which decay strongly with a lifetime of order 10 to the minus 24 seconds, were observed afterward. Probably the most famous observed QCD resonance is the gypsum meson, which was discovered in 1974. Nowadays, new resonances are being discovered. Hadrons with light quarks as well as C and B quark sectors are extensively studied. Some resonances still do not understood theoretically, among them XYZ states and LCB pentaquark candidates. Besides QCD resonances, the electroweak sector has resonances as well. As an example, the prominent resonance peak in the electron-positron annihilation corresponding to the boson is shown here. The second plot is from the CMS paper on the Higgs boson discovery, where the two-photon resonance is presented. W boson and top quark parameters are studied from the precise measurements of the resonance shapes. Therefore, a solid theoretical understanding of the physics in the vicinity of the resonance positions is required. What's going on near the peak position? The description of the processes with massive unstable particles suffer from the breakdown of the ordinary perturbation theory when the unstable particle is near its mass shell. Indeed, the propagator becomes singular. The singularity is usually avoided by resummation of the self-energy insertions. Such resummation renormalizes the mass, and the decay width appears naturally as the imaginary part of self-energy. The width is suppressed by the coupling constant. This simple consideration indicates on the Breit Wigner form of the resonance curves, which is used as a starting point to feed the experimental data. However, to identify all necessary terms in the calculation of a given accuracy is not a trivial task. For example, the box graph contributions are not included in the self-energy resummation. Selecting just part of graphs, the gauge invariance and unitarity of the theory can be spoiled. I would like to emphasize that these properties are valid only for the full amplitude at a fixed order. For precise extraction of the parameters from the resonance shapes, a systematic framework is required. Before going into more detail about such a framework, let's consider the way to test it. Fortunately, the inclusive cross-section of the line shape is directly related to the forward scattering amplitude by means of the optical theory. To test the effective field theory, we have to calculate the forward amplitude in the elastic scattering of two particles, which automatically gives us the inclusive cross-section. In case of the high energy scattering, the optical theorem looks very simple. Now I would like to turn to the main ideas of the effective field theory for resonant scattering. The common property of all resonances is the small bits in comparison to the mass. This property naturally suggests to select the ratio of width over mass as an expansion parameter. As we are interested in physics near the resonance peak, the hard momentum scale of order particle mass is integrated out and accounted for in the coefficient functions of the effective Lagrangian and the effective vertices by matching to the underlying theory. At the end, we work only with the soft scale modes in the effective theory. In the underlying theory, the elastic cross-section is enhanced in the resonance region due to the factor delta in the propagator of the unstable particle near its mass shell. The effective theory at leading order automatically resums such additional non-perturbative contributions to all orders in the coupling constant alpha and EFT parameter delta. We proceed to the construction of the effective Lagrangian now. The process under the consideration is a production of the resonance near its mass shell by two particles with a subsequent decay. Accordingly, the Lagrangian can be split into three parts. First part describes the resonance near its mass shell and the interaction with all fields in the model except for the external particles. It can be built similarly to the heavy quark effective theory. The second part describes the external particle sector. We are going to consider the scattering of highly energetic particles, and therefore this piece of the Lagrangian can be constructed in analogy with the soft collinear effective theory. And of course, there should be an interaction part to produce the resonance and to allow it to decay. We are going to follow the top-down approach, constructing the effective field theory. I would like to emphasize that the description above is valid for resonances of the arbitrary spin. Next, I'm going to concentrate on the simplest case of the scalar resonance. To illustrate the construction of FT, we consider the massive scalar resonance production by two highly energetic light fermions. The scalar and one fermions, which we call electron, are charged under the abelian gauge group, and the other fermion, neutrino, is neutral. The scalar can decay into the electron-neutrino pair through Yukawa type coupling. To have a gauge-invariant Yukawa coupling, the charges of the scalar resonance and electron are selected to be equal. The first line in the Lagrangian expression describes free scalar and fermion fields. The interaction with the gauge boson photon is obtained as usual, replacing the ordinary derivative by the gauge invariant one. The second line describes a free gauge boson field with a gauge fixing term. The third line gives the interaction terms, the scalar field self-interaction, which is for simplicity selected to be small, but needed for the renormalizability, and the counterterm part. The charged fermion mass is assumed to be small. However, in order to factor out the electron collinear infrared singularity into the electron distribution amplitude, the mass of the charged fermion should be kept non-zero. We assume it to be much smaller than all relevant scales and neglect in the Lagrangian. Now I'm going to describe three parts of the effective theory which are responsible for the production and decay of the resonance, the external particle physics, and the physics of the resonance particle near its mass shell. I start with the latter one. As we have already seen in the heavy quark effective theory and in exercises to this course, the soft scalar modes K describing the off-shell part can be encoded into the momentum wiggles of the massive particle with an on-shell momentum mv. After removing of the rapid spatial variations, a heavy scalar with the momentum near mv is described as a slowly varying field phi with positive frequency and conserved label of velocity. To construct the bilinear terms, we consider the propagator and expand its denominator near the complex pole position. We define the matching coefficient, a capital delta, which is given by the decay width in the polar normalization scheme, and use the perpendicular component of the soft momentum. In order to preserve the local gauge invariance after the separation on the soft and hard scales, we replace the derivatives of vector k by the soft covariant derivatives and obtain the Lagrangian part for the scalar resonance interacting with soft photon modes. Note that we keep only the leading terms in the expansion to perform leading and next to leading calculations in effective theory. Next, we are going to discuss the power counting. First, we organize the matching coefficient in powers of the expansion parameter. The scalar field propagator scales as an inverse power of delta. The integration of the four momentum adds delta to the fourth power. Consequently, we conclude from the propagator expression in the coordinate space that the scalar field scales with the power 3/2. Soft gauge field and fermion fields scale in the same way as the ultrasoft modes in soft collinear effective theory. This scaling can be also obtained considering these field propagators in the coordinate space. We present the leading bilinear terms in the first line. They both scale as delta to the power 4. I would like to draw your attention that the matching coefficient delta, which accounts for the hard scales, enters at the leading order and describes the summation of self-energy insertions and other graphs in a proper way. Terms in the second line are suppressed by one power of delta. The three photon and fermion fields scale as the soft resonance bilinear term. Advantageously, the effective theory approach allows to continue such a power expansion to whatever accuracy we want to achieve. Let's move on to the physics of external fermions. To describe a charged fermion moving with a large momentum p along some direction and minus, we need a collinear mode. The collinear momentum has an soft collinear effective theory scaling. The small component scaling is determined by the interaction with soft modes, and the perpendicular component scaling is obtained from the propagator pole. The Lagrangian for the neutrino field can be obtained replacing the covariant derivatives by ordinary ones and accounting for other direction of the neutrino propagation by interchange of n- and n+. As we are interested in the forward scattering only, we do not need to introduce two sets of modes for the initial and final particles. The power counting can be taken from the soft collinear effective theory or considering the propagators in the coordinate space. The leading Lagrangian scales as the second power of delta. Higher order terms can be also constructed, but they do not contribute to the leading and next to leading order of the resonant scattering in EFT. In addition, we are going to include operators that allow the production and decay of the resonance. Collinear electron and neutrino with a generic momenta produce a scalar, which generally could be far from its mass shell. The soft scalar modes could be produced by external particles with the specifically chosen momenta as it is shown here. It is useful to extract the large momentum as it was done for a heavy scalar and to deal with soft modes only. The Lagrangian is given by the first term of the soft collinear effective theory Lagrangian. The bilinear terms for the external fields scale now as the leading heavy scalar Lagrangian. It is convenient to integrate out the generic collinear fields and to keep only these external modes. The interaction part at the leading order contains terms from the Yukawa coupling of the underlying theory. At leading order, the coefficient C equals to 1. At next to leading order, we should account for the second term in the expansion of this coefficient. The NLO Lagrangian also contains an effective for fermion operator, which describes the production through the resonance far from its mass shell. For example, when radiation of the energetic gauge field by an electron happens. We have chosen the form of the Lagrangian to describe the resonance production at leading and next to leading orders. It contains soft photon and fermions, as well as a resonance field phi-v, external electron and neutrino modes psi n- and high n+. The Lagrangian deals only with the soft momenta scale. To make the predictions, we match our effective field theory to the underlying theory order by order. We are going to start from the leading order in effective theory. The only matching coefficient in the leading order is delta. This coefficient is obtained from the scalar particle self-energy graphs in the underlying theory. At the leading order, the self-energy is given by the photon loop contribution, the fermion loop with two Yukawa couplings, the loop with photon and scalar particle, as well as the bilinear in the scalar field counter terms. To look on the renormalization scheme dependence, we show results for the MS bar subtraction scheme and for the pole mass renormalization scheme in the underlying theory. At the leading order, only this simple graph with two Yukawa couplings and soft scalar propagator contributes to the forward scattering. Feynman rules are easily read off from the Lagrangian. For simplicity, we take the momenta of the external states to be a physical momenta, which is enough at the leading order. We obtain the leading order result for the scattering amplitude. To derive the line shape, we exploit the optical theory. The cross-section has a form of the Breit Wigner distribution. This behavior is universal for the leading order approximation of the resonant scattering with a heavy resonance. It was discussed also in the lecture course in context of the top quark decay. In our model, the unitarity cuts the fermion loop self-energy when the decay of the scalar resonance is kinematically allowed. Nevertheless, the effective Lagrangian is not real. The matching of the effective theory to the underlying theory guarantees that if T reproduces unitarity up to the desired accuracy. The leading order line shape is shown in the left plot in MS bar scheme by a dashed line and in the polar normalization scheme by a solid line. The difference is of the next to leading order. It is reduced going to higher orders of the perturbation theory. Plots correspond to the parameters in the right lower corner of this slide. The effective field theory description of the resonance is valid near the peak position. The unaccounted corrections are of order alpha and delta. Far from the resonance, the expansion parameter delta becomes large, leading to the higher order corrections of order unity. Effective field theory is not applicable anymore. However, the ordinary weak coupling expansion in the underlying theory is valid far from the resonance since there is no kinematical enhancements. In the intermediate region, which is bounded by gray vertical line in the right plot, both theories should be matched. Now I'm going to describe matching at next to leading order. The bilinear terms of heavy scalar field required to evaluate the two-loop self-energy in the underlying theory and determine the coefficient delta 2. The soft photon-electron interaction appears at next to leading order. From soft linear effective theory part we have to take only the leading term, as I have already mentioned. The contact term in the interaction Lagrangian can be easily obtained in the top-down approach, expanding the leading order S-channel scattering in powers of coupling constant. For the leading order result, we do not consider self-energy here. First term is included into the soft scalar propagator. For the head-on collisions, the second term vanishes, and the third one gives us a contact interaction. The coefficient C could be determined from the matching of the on-shell Yukawa vertex function. The FT part contains a correction due to the non-relativistic normalization of the scalar field. The vertex in the underlying theory requires the evaluation of the propagator residues and the leading order corrections to the 3-point vertex, which consists of the contour term and one graph with photon connected to fermion and scalar. Let's move on to the forward amplitude evaluation. On top of the leading order's forward scattering, the hard physics contribution is encoded in the corrections to the soft resonance propagator, vertex corrections, and the contact interaction. Soft physics contributes through the vertex corrections, resonance self-energy correction, and box graph. We choose the normalization scale and the collinear factorization scale such to avoid logarithmic enhancements. The left figure shows the change in the line shape going from leading to next to leading order. The ratio of the leading order shape to the next to leading order shape is shown in the right plot. The difference is around 10% at peak position and can rise up to 30%. The dependence on the normalization scheme decreases going to next to leading order. Also, the next to leading order result was fitted by the Breit Wigner form. The quality of such fit is shown in the right plot. This makes clear that the higher order corrections should be accounted for in the chosen form of the fit to the experimental data. I think this covers the main part. To conclude, we have constructed an effective field theory which describes the resonant scattering of two high-energy fermions with an intermediate scalar resonance in the S-channel. We made predictions for the leading order and next to leading order line shapes in this theory. The leading order line shape coincides with the Breit Wigner form, while to account for the next to leading order effects, the line shape should be fitted by other functional form. If T allows to systematically account for the gauge invariance and unitarity order by order and gives an elegant and correct solution for resummation of the kinematically enhanced contributions in the underlying theory. Effective field theory provides a well-defined calculation technology to describe the process up to a prescribed accuracy, which can be improved accounting for higher orders. The generalization to higher spin resonances and theories with a broader particle content is straightforward and consists from the same steps as this toy model with only technical complications. Thank you for listening. Following references were used during the preparation.